This video will be discussing a concept from Chapter 1 on orbitals and atoms. Now you may remember from general chemistry that we can write the designation for an element or an atom by giving its mass number A and its atomic number Z. So the atomic number is always going to be the number of protons, where the mass number is going to be the number of neutrons plus the number of protons. If we're to draw a simple diagram of the atom, we can always start with the Bohr model of the atom, where we have the protons and neutrons in the center. This is the nucleus, with shells of electrons around the nucleus. So in that case, we would have electrons kind of floating around on these designated shells around the nucleus. Remember that these shells are given the letter N, so this would be N equals 1, N equals 2, N equals 3, where a higher N means it's going to be farther from the nucleus. Now we know that this is not quite a great way to describe an atom, and it's definitely not a great way to describe the electrons, where the electrons exist in clouds. We can put that in quotes. They exist in electron clouds, or better known as orbitals. So orbitals are good designations of where the electrons lie in an atom. Remember, this is a probability function, so it tells us in general where we're going to find an electron at any given moment. It doesn't tell us exactly where we're going to find an electron. Heisenberg's uncertainty principle and Pauli exclusion principle tell us that we cannot know exactly where an electron lies, but this probability function will give us a good idea of where an electron is going to lie in an atom. So there's a couple different kinds of orbitals. The first one we're going to discuss is an s orbital. S orbital. An s orbital is given by a sphere. And if we cut right down the center of an s orbital, we'll see that the s orbital actually exists in concentric spheres. Now this is kind of tracks with what the Bohr model of the atom described, where we have we have concentric circles going out and further out. But this is a little bit more accurate. It's not concentric circles, it's actually concentric spheres. So what this would tell us is that this innermost sphere is n equals 1, then n equals 2, then n equals 3. As we move further out, we're moving both higher in energy and further away from the nucleus. Our second type of orbital is going to be our p orbital. Our p orbitals are higher in energy than s orbitals, and there's 3 of them. So they're shaped like dumbbells, where one side is in an opposite phase of the other. If we put this on an axis, we can see that one will be facing along. We would call this the px orbital. If we put an axis and point it along this way, we could see that that's a pz orbital. And if we point one directly up and down, we could see that that is going to be a py orbital. Now these 3 orbitals, since there's 3 of them and they're the same energy, we call these degenerate. And degenerate orbitals are always going to be at the same energy level. So if I'm filling in one electron into a p shell, there's no preference for whether we're going to px, pz, or py. Since these are degenerate, they're all going to be at the same energy, and there would be no preference. Keep in mind that this trend for a number of orbitals within a shell, so for tracks all the way up to f. So an s orbital is going to have 1, or an s shell is going to have 1 orbital. A p shell is going to have 3 orbitals. A d shell is going to have 5 orbitals. And an f shell is going to have 7 orbitals. The shapes of the d and the f shells are less important for this course, since the organic molecules usually don't engage with their d or their f shells. But if you go into further chemistry classes where you're dealing with metal-based orbitals, you will see d shells and f shells being engaged. Keep in mind that just like in the p orbitals, the d shell and f shell, those 5 and 7 orbitals, are going to be degenerate as well. So when we're filling in, say, a d shell, these 5 orbitals there's no preference for which one this first electron will go in. They are equally at the same energy, so there's no preference. Now, when we're talking about atoms achieving a configuration that makes it the most stable, we are looking to be isoelectronic with a noble gas. So what does that mean? Isoelectronic with a noble gas means that the atom has same number of electrons as a noble gas. So let's look at an example. So let's look at oxygen for an example. So oxygen, the electron configuration of oxygen is 1s2, 2s2, 2p4. If we were to draw an orbital diagram, we could put 1s2. So this would be our 1s. So it would have 2 electrons. We then have 2s. And then we have 2p. And remember, these are degenerates, so there's no preference for which one's going to go in. So we have 1, 2, 3, 4. Remember that when we're filling in orbitals, we're filling in a degenerate set of orbitals with electrons. They'll always spread out before they start pairing. This is energetically favorable. So if we're to achieve a noble gas configuration, we want to have 8 electrons in the valence shell. If we're looking at the valence shell here, we see that the 2s and the 2p make up the valence shell. So that means that we have 1, 2, 3, 4, 5, 6 electrons in the valence shell as oxygen as an atom. But in order to get 8, we would need to gain 2 more. Sorry, this should be a down. So in order to gain 2 more electrons, we would obtain the ionic configuration of O2-. If we're gaining electrons, we're going to form an anion. That would give us the configuration of 1s2, 2s2, 2p6. And if we look at the orbital diagram, we would have 1s2, we'd have 2s2, and we have 2p, 1, 2, 3, 4, 5, 6. So we're now isoelectronic with a noble gas. The valence shell has 8 electrons. So we would say that this is the most stable ion of oxygen. This traces for any of the nonmetals and the metals. So for instance, if we were looking at lithium, we would see that the atomic configuration of lithium is 1s2, 2s1. So we would get an orbital diagram of 1s2, 1s, and 2s1. Our valence shell has 1 electron in it. Now in this case, we could say gain 7 electrons to make a isoelectronic with neon, but in this case it would be much more stable to lose 1 electron and form an Li+. Remember, if we lose electrons, we're forming cations. So Li+ would have the configuration 1s2, and we would be left with the orbital diagram of 1s2. So if we look, O2- is isoelectronic with neon, and lithium plus will be isoelectronic with helium. This is what makes this stable. It's because it is isoelectronic with a noble gas. Just 2 things to note when you're filling in orbitals, or when you're talking about orbitals in atomic chemistry. Orbitals will fill in increasing energy. So that means you'll go 1s, then 2s, then 2p, then 3s, then 3p, etc., etc., etc. Remember, there's a couple exceptions to that rule where, for instance, 3d gets filled before 4p. Just remember, I would review Gen Chem if you have any challenges with that. Just remember there are a couple exceptions to that rule. And as I mentioned before, degenerate orbitals will contain 1 electron before pairing. That's what we did up here with oxygen. We went 1, 2, 3, and then 4, so we're going to spread them out. This is energetically favorable. It's called spin pairing, and this will actually cause the energy of the atom to go down overall, whereas if you paired it before you spread them out, then it's going to be higher energy. And this is kind of goes without saying. There's only a max of 2 electrons per orbital, and they must be opposite spins. So that means that something like this is good, something like this is no good, and something like this is also no good. You can only have a maximum of 2 electrons and they must be spin paired.